Great. I will say welcome, a formal welcome to all of you here. My name is Dawn Salerno. I am coming to you from the Roach Jones Duff House and Garden Museum. It's sometimes hard to remember where we're coming to you from since we're all on our computers. I'm actually at the museum itself, and I'm happy to have you here. So thank you for being here. I just want to let you know that we are doing virtual programming just actually through early May, and then we are lucky enough to be able to move outside. We have a beautiful garden here, and our future programs will be actually at our site outside throughout the summer into the fall, in fact, where it's just lovely to be. So I will drop our calendar into the chat. That's where you can check out our future education programs. We hope you will check out all we have to offer. We actually offer quite a range, and outside, once we're outside, we can do larger performances. So we have music planned, we have a Shakespearean play planned for August, all sorts of great stuff going on here at the RJD. I also want to give some thanks. Certainly thank you to you all for being here, for coming tonight. I want to thank the board of directors of the RJD. It's actually a board of trustees at the RJD. They're wonderful supporters. They help me so much in my work here. I want to thank the staff, our small but mighty staff, Rick Finneran, Jessica Serpa, the very new Jill Conley, and Isabel D'Souza. They're just wonderful help to me. And thank you, donors and members. Some of you are probably tuned in tonight. Thank you for all your support of the museum. With that, I want to introduce our speaker and remind you that we will take questions at the end. I hope you'll stay tuned so that you can hear the full talk, and also stay through to questions at the very end. Our speaker tonight, I'm very grateful to have here, is Dr. Peter Raymond. He's professor of Ecosystem Ecology at Yale University in New Haven, Connecticut. His research focuses on the chemistry and ecology of inland waters. Dr. Raymond is currently editor-in-chief of the American Geophysical Union's journal Global Biochemical Cycles. Dr. Raymond received his BS from Marist College and his PhD from the Virginia Institute of Marine Science, College of William and Mary. He is a fellow of the American Association for the Advancement of Science, a member of the Connecticut Academy of Science and Engineering. He received the Coastal and Estuarine, I know estuary, I don't know if I pronounced estuarine. Estuarine, thank you. Research Federation's Cronin Award for Young Scientists, and is a ISI highly cited author. So I've also been told he's quite entertaining and funny by somebody that knows him well. So with that, I'm going to relinquish the spotlight to him, and we will get started.
Okay, perfect. Thanks, Dawn, and thanks to the RJD for this invitation, and thanks everyone for showing up. I'm going to talk today about the physical science of climate change. I teach a course here with the same name at Yale, actually teaching it right now this semester. Real quick slide about me. As Dawn said, I'm trained as an oceanographer. My research focuses on the chemistry of streams and rivers in the near coast. And this work has always included measuring the amount of greenhouse gases in these water bodies and trying to understand how much greenhouse gases are exchanged between them and the atmosphere, which is sort of my tie into climate change research. What I'm going to do today is I'm going to try to do a few things. I want to give everyone sort of a brief introduction to climate science, sort of the fundamentals of climate science, but I want to do that through the lens of history. So sort of discuss when major components of climate science were first discovered and introduced to the science. And I want to also do that by providing some sort of local reference for when that time was. And I'm doing that today with help from Michael Dyer from the New Bedford Whaling Museum, who provided me with some photos and paintings. Then, depending on how we're doing for time, I'll talk a little bit about sort of the status of CO2 pollution today. And so my strategy for doing this is to shed some light on the physical science of climate change, some of the scientific underpinnings, but also to let folks see that this science is based on first principle chemistry, biology, and physics, and is actually worked out a long time ago, right? Sort of dispel this sometimes political components that are introduced into the discussion. Okay, put on my laser pointer here. So we receive, the Earth receives its heat or its energy from the sun. And so all the warmth that we, see in the Earth's energy budget originates from the sun. And there's a couple of interesting components to this. One is that the energy that comes from the sun comes in a very short wavelength, right? Remember wavelengths back from physics. And it's shown in this little figure here where the distance between the waves for this energy coming from the sun, centers at around half or 1 micron. So 1/1,000,000th of a meter is the distance of these wavelengths, and that's also where visible light is. So this energy comes from the sun in this very short wavelength. And one of the key components of that is the atmosphere, aside from clouds, and the atmosphere is mostly invisible to this short wavelength radiation. So it's allowed to sort of pass through the atmosphere unless it hits a cloud, and it can be reflected back to space. It can also hit components of the Earth, particularly white components like glaciers and ice, and be reflected back to space also. So the first component of the Earth's energy budget is this really short wavelength radiation that's coming through the atmosphere and being absorbed by the Earth's surface if it makes it there. The key component is that when this energy is, after it's been absorbed, emitted back to the atmosphere, it's emitted as long wavelength radiation. So as you can go back to this graph up here, the wavelengths are about 10 to 100 times larger, so 10 to 50 microns. And so it's emitted as this long wavelength radiation. And the important part of this is that the atmosphere is not invisible to this long wavelength radiation. There are things in the atmosphere, notably greenhouse gases, which can absorb this long wave radiation and reflect it back down to Earth. And this is the greenhouse effect, right? This trapping of long wave radiation and sort of recycling heat and energy in the Earth, making it habitable, basically. We didn't have this greenhouse gases trapping this long wave radiation, it would be too cold for life, right? The Earth would be an ice planet. And so this is one of the, primary components of physical science of climate change, is this idea that you have energy coming in from the sun in this short wavelength, absorbed by the Earth, re-emitted as long wave radiation, which can be absorbed by things in the atmosphere and trapped, right? Like a greenhouse. The same thing happens in a greenhouse where the short wave radiation can pass through the glass, but the long wave radiation gets trapped trying to get out. And this basic idea, or this conceptualization of the Earth's energy budget, was first articulated by a French scientist in 1827. His name was JeanBaptiste Fourier. If you can sort of reach back to your high school physics, you might recognize that name, because he was best known in science for his representation of sine waves mathematically, right? So he was interested in waves and wavelengths. He described them mathematically for the sciences, and he was very interested in heat conduction, not necessarily focusing on the Earth's heat budget. But he wrote this paper in 1827 using this sort of advanced knowledge base he had of heat transfer and discussed the overall heat budget of the Earth. And it was kind of remarkable because, you know, we had just sort of figured out that there was this long wave radiation just a couple decades before. This wasn't when scientists had, you know, really complicated labs that they could use to make measurements to sort of confirm their ideas and their hypotheses. There were a few measurements of some folks working out in the Alps with something like a greenhouse where they had these glass houses and they were putting in substances of different color, right? Substances that would absorb more and long wave radiation, and seeing how it changed the temperature of these greenhouses. But he concluded in this paper that the heat emanating from the sun is different from the heat emanating from Earth's surfaces, and postulated that the atmosphere trapped this heat that was this long wave radiation coming off the Earth. This is in 1827, right? A period of time where, you know, most of us don't really have a reference for. Michael Dwyer shared this painting of the New Bedford Harbor. You know, this I think was a few years after 1827, during a particularly cold winter when the harbor froze over. I like to think about, you know, this 1827, John Quincy Adams was president, right? And so with respect to U.S. history, you know, that's our ancient history, right? It's going back pretty far. In the sciences, it was also when the ideal gas law was formulated. And disregard this, I made an error here with the first New Bedford High School. That's with a later date, obviously. But it was when the ideal gas law, PV equals nRT, was formulated in the sciences. Okay, so 1827, we've sort of worked out this idea that there's long wave radiation and that there's substances in the atmosphere or things that could perhaps trap this long wave radiation. We now know, right, there are these three major greenhouse gases: carbon dioxide, methane, and N2O, right, that are present at low concentrations in the atmosphere. We'll see some of those concentrations later, but are particularly efficient at trapping this dark radiant heat that Fourier discussed. Basically, we now know that if these greenhouse gas concentrations increase, more radiation can be trapped. And this trapping warms the lower atmosphere, what scientists call radiative forcing. There was an Irish scientist, physicist in the 1860s who started to figure out, you know, which of the atmospheric gases absorb heat. His last name was Tyndall. He studied the molecular physics of radiant heat. So you can again sort of see how his background sort of made a natural segue into this sort of studying of the Earth's heat budget and greenhouse gases. He did have a laboratory, and he put an immense amount of time improving the measurements of the absorption of long wave radiation by different gases. In particular, spent some time improving this instrument called the galvanometer, which is what measures electrical current. So these improvements allowed him to make these measurements of small changes in energy and current at the low concentration that greenhouse gases are found. And so he demonstrated that a few gases and things like water vapor, that as their concentrations went up, they were able to trap more of this long wave radiation. And this is in 1861, and John Tyndall has long been sort of credited with making this contribution to climate science. Just recently, credit has also been given to an amateur woman scientist from Connecticut, Eunice Foote. Eunice Foote was sort of an amazing individual. She was also present at the first Women's Right Convention in Seneca Falls, which was in 1848. She used these glass cylinders, which she encased with a mercury thermometer, and again started adding different concentrations of gases, in particular, varying the concentration of carbon dioxide in these glass cylinders. And she wrote in her paper that's shown here on the heat in the sun's rays that the receiver containing carbon dioxide became itself much heated, very sensibly more than her sort of control flask. And on being removed from the sun, it was many times as long in cooling. She didn't articulate the role of long wavelength radiation, but is now credited as being the first person to say in print that if carbon dioxide levels were higher, the planet would be warmer. And this is now being recognized for the important accomplishment that it is. Historians feel like Tyndall was probably unaware of her work. At the time, he was in Europe, where most of these, more prominent scientists were, and there was, not the communication there is between the continents and scientists that there is now. But she also was an amateur scientist, and amateur scientists were kind of looked down at, but also as a woman in a field that has long had trouble recognizing the contributions of women to science. So this was in 1860, and Michael Dyer provided me with this photo of this really cool sort of long sort of rendering of the New Bedford Cordage Company in around the same time period, 1860. And so you can sort of get a feel for what the surroundings of New Bedford looked like. Of course, in the 1860s, the Civil War was going on in the US. This was also the time when Gregor Mendel sort of conducted his famous tests on pea plants to form the laws of inheritance in Austria. And so at the time where Eunice Foote and Tyndall are making their measurements, Gregor Mendel is growing his pea plants, making these findings for genetics. This is also the time of the largest fire in New Bedford history, right? Fire that burned a lot of Water Street, destroyed most of the shops on Water Street, and worked its way all the way up to North Street and 2nd Street, and took out a lot of the buildings on the wharfs in New Bedford. It was shortly after this that New Bedford bought its first sort of fire truck, or, they didn't call them fire trucks back then, but okay, so it's 1860s. We've figured out what the Earth's energy budget is, sort of what's driving it. We now understand that there are greenhouse gases that are important to it, and that CO2 is one of them. But this really isn't enough to understand the Earth's climate system. The temperature of the Earth is not just dependent upon energy coming in from the sun and the concentrations of greenhouse gases alone. There's sort of this complex interplay between things like the surfaces which absorb radiation and reflect radiation, like ice, and other components of the atmosphere's chemistry and the carbon budget of the Earth. And so in our class, we like to say that, you need to understand things about the land and how the land interacts with shortwave and long-wave radiation, how it can take up or emit greenhouse gases. Similarly, the chemistry of the atmosphere, of course, the oceans, and we'll talk a little bit more about this at the end of the talk, and the cryosphere, or the ice at the Earth's pole, is particularly important. But not only that, you need a model to be able to tie these different components together to try to predict the Earth's climate system and how it will react to perturbations like increasing the greenhouse gas concentration. The first climate model was developed in 1891. It was created by a famous Swedish scientist named Sven Arrhenius. Again, Arrhenius is more famous for other contributions he made to science. In particular, some of the equations that describe the impact of temperature on chemical reactions are credited to Arrhenius. They're called the Arrhenius equations. So again, you can see that his fundamental interest in science, or sort of what made him famous, or his bread and butter, was describing the impact of temperature on different processes. He was also, one of the earlier directors of the Nobel Institute in Sweden. But he performed what we call the first climate sensitivity calculation. And what that is, a climate sensitivity calculation just asks a simple question: how will the Earth's temperature change if we double the amount of carbon dioxide in the atmosphere? And so you have to produce a model, like I said, to be able to perform that calculation. And again, his model was, pretty advanced for the time. He had sort of absorption coefficients that he had to figure out for the different gases. How efficient are they at trapping heat? He had to try to figure out like how much ice there was in the planet and how it reflected shortwave radiation from the sun. Something called the water vapor feedback, which is basically, as you warm the planet, you evaporate more water off the oceans, which can trap more heat. And then how this heat moves around the planet, which is important to the Earth's climate system. And remarkably, Arrhenius got an answer that was pretty close to right. He predicted that if you doubled atmospheric CO2, you'd warm the planet by 6 degrees Celsius. We now feel that that number is like 3.5 degrees, but that's pretty close. It's sort of debated how lucky he was, because there were some, risky assumptions that he made. Unfortunately, he also predicted that it would take 1,000 years to double atmospheric CO2, so he didn't think it was an immediate concern. Basically, at this time in 1891, we had started burning coal and removing a lot of the Earth's forests. And so he knew we were adding CO2 to the atmosphere, but he assumed that it would be added at the same rate moving forward. He didn't imagine a world where we could add as much CO2 as we're adding now. So he thought it would take a long time to double atmospheric CO2. So it was more, this paper was more interesting from sort of a geologic time frame, trying to understand Earth's climate in the past. But this is 1891, our first climate model and our first climate sensitivity calculation. In 1891, the landscape of New England is fairly still unrecognizable to what it is today. This is a view, you're sort of looking out at the New Haven, the New Bedford Harbor, in a painting by Clement Nye Swift. And here's another sort of rendering of the Morse Twist drill factory, right, which was important to the New Bedford's history for a long period of time. It's also around when Marie Curie arrived in Paris, began her work on uranium isotopes to try to put it in perspective of what's going on in science. In New Bedford, electric trolley cars replaced horse cars around this time. And sort of as a shout out to my Uncle Richard, right? It's when the Lizzie Borden trials began in the area, which most of us have sort of some frame of reference to if we grew up in the area. So that's 1891. Still, 130 years ago. It wasn't until 1938 that became a little more apparent that we were adding, enough CO2 into the atmosphere to increase the concentration of CO2 in the atmosphere. This was done by another amateur scientist, Guy Callender. He was a U.S. steam engineer and inventor, sort of an amateur climatologist. and he wrote this paper called The Artificial Production of Carbon Dioxide and Its Influences on Climate. He was able to sort of go into the literature and come up with a few measurements of CO2 sort of at the turn of the 20th century and then 30 or 40 years later, and conclude that within the instrument record, even though our ability to measure this was not great at the time, that CO2 concentrations were going up. He also looked at some weather stations and thought he could see, an early indication of an increase in temperature. Guy Callender also sort of discussed the future, but made the same mistake that Arrhenius made, and he assumed constant emissions over time. That is, he assumed that moving into the future, if we emit CO2 at the same rate that we were emitting it at the turn of the 20th century, that this didn't seem like an issue. However, his papers were influential with respect to scientists that came after him, and that is they wanted to sort of move forward and make some more precise measurements to try to see, if we could get to the bottom of how fast concentrations were going up. Of course, the biggest thing for 1938 around us was the hurricane of 38, whose eye passed over Connecticut, and this hurricane came as a sort of complete surprise to most folks living in New England. This is a picture of Providence during the hurricane. And for me, we're starting to get to a period of history where I can make connections, right? I remember my grandmother and others talking about the hurricane of 38. It was something that was left a mark, so to speak. And you can also see that this is an aerial view of the harbor around that same time, and you're starting to get to, a New Bedford that's recognizable to what we see today. So it was around this time where, the scientists published the first paper sort of saying, hey, we can see this concentration of CO2 going up in the atmosphere, the records that we have. If you want to go again back now to high school biology, it was also when the Krebs cycle was first articulated, the complete cycle, right? This process for when we put energy into ATP that some of our high school biology teachers made us memorize. And so that's sort of the, sort of a benchmark with respect to science. Okay, so this is the last one with respect to sort of the history, some of this climate change science. And this is perhaps one of the most famous graphs in climate change science. It's called the Keeling curve. It's from a scientist named Keeling, who put up a station on the top of a volcano in Hawaii. He did this because it's high enough up where it's sort of out of the range of disturbance. The atmospheric chemistry is fairly clean. And he started making measurements of CO2 every day. And he did this accurately. And so his first concentration measurement made in the late 1950s had a CO2 concentration in the atmosphere of 313 parts per million. And as you could see, as he's there making these measurements in Hawaii, it didn't take many years for him to be able to see through his own measurements that CO2 was going up in the atmosphere, sort of in real time, right? You can make a measurement and basically measure a CO2 concentration on average, if you're making these measurements every day, that your concentration this year is higher than the concentration last year. These measurements have been continued. You can also sort of see the breathing of the continents or the breathing of the globe in his measurements, where you have the highest concentrations of CO2 in the northern hemisphere in our winter, when there's no plant photosynthesis, and when the plants come out, they consume CO2 to build their biomass. Concentrations in the atmosphere reach a low. So you can see the sort of influence of biology on atmospheric chemistry. But Yeah, there were a couple of papers early on where he was able to show that CO2 concentrations were increasing undeniably in the atmosphere. This is in the early 60s. I was able to dig up this postcard of New Bedford from the early 60s. Maybe some of you can recognize some of the stores in there. With respect to science, it's when Rachel Carson published The Silent Spring, right, which was raising the alarm on another environmental problem, right, the spreading of DDT around the environment. It's also when the laser is invented, right, so it was the first time that someone provided like a coherent light ray at the same wavelength, fully in phase. And so, you know, by the 60s, so 60 years ago, scientists knew this was an issue, right? And knew the concentrations were going up, and it worked out that, in fact, you know, they were going up at a rate that was alarming with respect to the potential for impacting the Earth's climate. So it's been 60 years, basically, since scientists have been raising the alarm about this issue. Just to draw your eyes to this, the concentration of CO2 now is over 400 ppms, 400 parts per million in the atmosphere. I wanted to show this one graph of the CO2 concentrations in an ice core taken from Antarctica. These ice cores are pretty remarkable, because what they do is sort of the ice almost sort of lays down layers like a tree ring, sort of, and they trap bubbles in the ice. And if you dig down, you can actually extract the gas from those bubbles and make direct measurements of CO2, at least in the Antarctic ice cores, to work out what CO2 concentrations were going back further in time. This is a famous ice core called the Vostok ice core. It's 4 kilometers deep, so they're drilling out 4 kilometers of ice and measuring CO2 in the ice cores. And by going down 4 kilometers, you can basically go back almost 1 million years, 800,000 years. And the concentration of CO2 is varying in this time. These are the ice ages, where you have low CO2 concentrations when the ice is at its maximal extent, and highest concentrations when the ice recedes. And the reasons for these cyclical changes in CO2 are partially due to changes in the energy coming from the sun, but then also due to responses in the Earth's climate system with respect to changes in the climate system. And so there are a lot of things you can use this graph for, but one of them is you can sort of show that for the last 1 million years, CO2 concentrations have never been higher than 300 ppm, right? I just said we're at 400 now. So we've pushed the concentrations of this greenhouse gas to a concentration that we haven't seen in at least 1 million years. And it seems like potentially for 10 million years. You can look up here, we can't get direct measurements of temperature from these ice core. These are worked out through what we call proxies for temperature. But the scientist's best guess is that over the ice ages, the average temperature of the globe varied by about 10 degrees Celsius. So with less than 100 ppm changes in CO2, very small changes in the amount of energy coming from the sun, the temperature of the Earth is changed by 10 degrees. This is sort of another sort of interesting graph to look at. It's now just the last 2,000 years. And what we're seeing here is, instead of CO2 concentrations, is what the temperature has been of the Earth over the last 2,000 years. And this is sort of the famous hockey stick graph that was first published by Michael Mann, who's the publisher of this paper here also. And these concentration of CO2 is determined a bunch of different ways, right? We have thermometers that came on in like the early 1800s, but then there's things like tree cores, right, where you can look at the tree rings and work out temperature. Coral reefs or have something similar to a tree ring, and we can look at the chemistry of those and try to check out the temperature differences of the water that the corals live in. And you know, to our best ability with this large amount of uncertainty, the temperature of the Earth is now warmer than it's been in the past 2,000 years. Certainly, you can see the instrumental record. You can see it better here in this bottom blow up of this graph, where it's gone up quite unarguably over the past 100 years. And so CO2 is going up, temperature's going up as predicted by these scientists, you know, that have been working this out for the past couple hundred years. So I'm just going to talk now for like 15 minutes or so, leave plenty of time for questions about where we are with CO2 pollution now. There's a large number of scientists, including myself, who are trying to understand, you know, how much CO2 we're putting into the atmosphere every year, where it's going, how it's interacting with the oceans and the atmosphere. And so I just wanted to introduce you to some of these numbers. Okay, so there's a few different ways you can look at this, but basically there's two ways that humans pollute the atmosphere with carbon dioxide. One is through burning fossil fuels, coal, oil, natural gas. The other is through chopping down tropical rainforests, mostly for pasture. We measure the amount of CO2 we're adding to the atmosphere through these processes in this term called gigatons. And this is a really hard number to try to conceptualize or understand. A gigaton is 1 billion tons, or 10 to the 15th grams of CO2. I've tried a lot of different ways to try to figure out a way to articulate how big this number is, and I think it's just so large that it's really hard to conceptualize. One way to think about it is that if you took every person who lives in New York City, 10 million people, and turned them into the weight of Statue of Liberty, that would be a single gigaton. But I don't really think that's that meaningful really either. Each US citizen is responsible right now for about 16 metric tons of CO2 pollution per year. So if you can start to think about what a ton is with respect to weight, and you can imagine each of us is responsible for 16 metric tons, right? We're not really responsible for pollution on that scale of anything else, but it's a massive issue. And part of the issue is that this is invisible pollution, right? You don't see this coming out of your tailpipe or your exhaust. It's invisible. But nonetheless, you know, so as a globe, we're putting about 40 gigatons of CO2 pollution into the atmosphere every year. Half of this builds up in that keeling curve, or results in additional atmospheric CO2 from year to year. So that's a sort of a good part of the story. Only half of our pollution leads to this CO2 buildup in the atmosphere where it can be a greenhouse gas. The other half is either taken up by the world's forests or is taken up by the ocean through sort of natural processes of plant growth, or just diffusion of atmospheric carbon dioxide into the ocean. And so this is, you know, can be seen as a service that these ecosystems are providing us. I'll talk a little bit more about them. Unfortunately, with respect to ocean uptake, it's also troubling, because this is CO2 in the ocean is a weak acid, and you might have heard of this sort of other component of CO2 pollution, or ocean acidification, and that's due to this ocean uptake of CO2. Here's another way of looking at this, and this is a slide from my class that we go over early on in the semester. That is, if you want to understand the atmospheric growth of CO2, all you need to know is how much CO2 we're adding from fossil fuels and the burning of forests, how much is taken up by the land sink, and how much is taken up by the ocean sink, right? And so that's the equation. It's just simple sort of checkbook arithmetic, where the emissions of fossil fuel and land use change is equal to growth in the atmosphere versus plus storage in the ocean plus storage on land. And then there's this thing where, you know, when you ask scientists from each of these sectors to provide you with numbers, the budget doesn't quite close. And so there's this fifth term called the budget imbalance. So let's just talk about these a little more, and then we can open it up for questions. This is how fossil fuel emissions have looked through time. And so one of the real issues and problems here is basically each year we emit more CO2 to the atmosphere than we did the year before. So we're polluting still more and more CO2 each year, right? We still haven't, we've heard a lot about, with respect to COVID, bending the curve. We still haven't really bent the curve with CO2 emissions. So we know this is a problem, right? Governments are actively starting to work on this, but we're not, you know, we have to get to the point where we almost get to zero emissions, but we're not yet at the point where we have can say that we've emitted less this year than the year before, except for 1 year. When you went from 2000 to 2009, it wasn't a statistically significant decrease, but this is basically the decrease in CO2 emissions with the economic downturn of 2008. So these emissions are tied to the global economy. There are a few countries that are responsible for most of the emissions. The US, right? We're responsible for a large amount of emissions. The European Union, they've bent their curve a little bit. And the companies with emerging economies have been seeing the largest increase in emissions over time. It's China and in India. However, if you dig more into these numbers, some of our emissions in the US and in Europe, we've outsourced to China. They produce our goods. In producing these goods, they produce emissions. And so the way this accounting works, they get counted for the emissions, even though our consumerism is sort of driving some fraction of these emissions. This is where the CO2 is coming from. You can see that we have started to bend the curve a little bit on coal. Coal is expensive. It's expensive to dig out of the ground. It's also, you know, has a lot of other negative impacts on the environment, particularly mercury pollution and particles in the air that impact human health. So coal will probably, you know, be the largest decrease over time as we move forward, because it's so expensive and can't compete as well with these other forms of fossil fuels and you know, emerging alternative sources of energy like wind and solar. However, oil and gas have been going up over time. This is a graph that's showing the amount of emissions coming from the burning of tropical forests going back the last 60 years. This has remained pretty steady. It's not increasing or decreasing. You know, the globe is actively trying to decrease the loss of tropical forests. So there's also hope that progress can be made on this in the near term. And this shows these emissions going much further back in time, right? So here's that land use change, burning of the forests, you know, back in the 1880s when Arrhenius was coming up with that climate model. Most of the emissions were from burning a forest. There was a little bit of coal, right? We figured out coal in like the 1860s. And you can see the sort of emergence of oil in the 50s or 60s and a great growth in oil use over time. This is how they played out over time. This is really interesting though. So this is showing some of the things I've been discussing. So the burning of fossil fuels increasing over time, right? Maybe, you know, hopefully we'll be able to bend the curve in the near future. Not much change in land use change. The atmospheric CO2 is going up, right? And it's going up at a faster rate now than it did in the 1960s because we're burning more fossil fuels. But one of the remarkable thing about the Earth's carbon budget is that this land sink, or the amount of CO2 being taken up by land, and this ocean sink, or the amount of CO2 being taken up by the oceans, is also increasing, right? And with respect to the warming of the atmosphere, these are positive things. They're particularly the land sink. There are, you know, hypotheses on why this is occurring. But one of sort of, you know, an additional worrisome component of the climate budget is there are feedbacks in the climate systems where you can predict that these sinks on land and the ocean will start to decrease over time. And if that occurs, atmospheric growth will be even faster, right? Assuming fuel input to the atmosphere doesn't change. And so there's, you know, right now, as I said, the land and the ocean take up about half of fossil fuel emissions. There are reasons why that proportion could go down over time. I'll just kind of wrap up and repeat some of the points I wanted to make. There is a book called The Warming Papers, which goes over some of those earlier papers I discussed and more in detail, and is you know, an interesting read if you're interested in this. But you know, this basic idea that CO2 is a greenhouse gas which traps heat in the atmosphere, or it's based on first principles of physics, chemistry, and was worked out centuries ago, right? And so this you know, this isn't debated science. It is science that was worked out based on first principles. The concentrations of CO2 in the atmosphere are now higher than they've been in the last 800,000 years, right? We know that from those ice cores. And this is causing warming that we're measuring in the planet right now. We're still adding 14 billion metric tons of CO2 to the air every year, half of it of which is building up in the atmosphere from year to year, leading to this warming. So I will stop there and see if I can get back to Zoom and stop sharing my screen. And yeah, if folks have questions of any type, I'm more than happy to do the best I can in answering them.
Thank you so much, Dr. Raymond. And I would invite people to put their questions in the chat. I will read them for you if you prefer, or you can unmute and ask your own question to Dr. Peter.
Yeah.
Whatever you prefer. I'll keep my eye on chat. They're just in awe. They're soaking in all the data.
Peter, I don't know if this is Joe Maggio. I don't know if this is my background, but I was actually sitting here taking notes.
Awesome.
I have one question, and that is, how much do volcanoes contribute to putting carbon dioxide into the atmosphere?
Yeah, that's a great question. So like I said, we can say that we add about 40 gigatons of CO2 in the atmosphere with fossil fuel burning. A long-term average for volcanic emissions is about 0.5. But of course, that's highly variable. It depends on, the number of volcanic emissions from decade to decade and century to century. So they do add CO2, and they're important if you start to think about that really long-term CO2 budget and like glacial variability and stuff like that. But with respect to the present day carbon cycle, they're kind of in the noise.
Okay, thank you.
The cool thing about volcanoes is what they do is they add a lot of sulfate aerosols, which reflect shortwave radiation. And so you can go back in time and see when volcanoes erupted, and the Earth's temperature are generally cooler because of all these sulfuric aerosols that volcanoes emit into the upper atmosphere. And so in fact, one of the geoengineering solutions that scientists are starting to think about is to mimic volcanoes and emit these particles into the upper atmosphere as sort of a last, a last ditch effort to cool the planet if it gets to a point where it's becoming inhabitable.
We've got 2 questions in the chat. I'll start with
Yeah.
Rick's. Rick asks, what is the best path forward in regards to options in fuel and land management?
Yeah, so, we basically have to wean ourselves off of fossil fuels. And this is possible. So alternative forms of energy are going to have to become dominant. So things like wind and solar. And with land management, there are some ideas of trying to manage land to increase that sort of CO2 uptake in forests. It's possible, small part of the solution, but there's no solution without really weaning the population, the world's population off of fossil fuels. Great question.
And we have another one from Stuart who says, I'm curious whether there was a COVID downturn in CO2 like in 2008. Also, how do the tons of CO2 compare to tons of plastics?
Yeah, so there was a COVID downturn, particularly during, around this time last year, because transportation is one of the large sources of CO2 to the atmosphere. And so for a number of months, you could see a decrease in the CO2 emissions. I don't know what the final number was. I actually had a slide in there in case this question was asked, but yeah, there certainly was a downturn, but I don't think we're expecting, like a large percentage decrease in global emissions. It'll be a small percentage change because it was only transient, just a few months. Great question. Oh, and plastic. We measured tons of plastic in teragrams, so 3 or 4 orders of magnitude less than CO2. So much, much, much smaller.
Any other questions from the live audience? You're welcome to pipe up or write in the chat. Family reminiscing from friends.
Peter, it's Joe Maggio again. And
Yeah.
I understand your point on what we could do with the land sink, but is there anything we could do with the ocean sink?
Yeah, so the ocean sink is interesting, partly because some of the technologies that scientists are thinking about to try to remove CO2 from the atmosphere doesn't remove CO2 from the oceans. And this, this idea of ocean acidification, it would be great to have another talk where we just focus on that. But there's fewer sort of solutions to ocean acidification. There are ways you could sort of try to counteract the drop in pH that CO2 uptake of the ocean has has created, and it's basically like trying to seed the ocean with things like limestone. I guess similar to what organic gardeners might do to increase the pH of their soils. In fact, that's another engineering solution that scientists are considering, trying to increase the amount of limestone and silicate minerals that are put out over the Earth's surface, because when they dissolve, they consume atmospheric CO2. Yeah, ocean acidification is a really interesting and tricky one because pH is so important for so many different things. You know, it's like one of these governing variables, and you know, the ocean scientist colleagues are very alarmed about the acidification of the ocean, and it's just a pure physical process. As you put more CO2 in the atmosphere, concentrations get higher. Concentrations in the atmosphere are higher than the ocean, and they just diffuse. CO2 just diffuses in across that concentration gradient. And if we stop emitting CO2 to the atmosphere right now, this is what's going to equilibrate or draw out the CO2 from the atmosphere over time. Is just this equilibration process with the oceans. It's just a natural sort of physical process.
Well, I want to
Thank you, Peter. And
Yeah.
hello, Irv, and hello, Paul.
Yeah, good seeing everyone.
And I want to thank Peter, Dr. Raymond as well. We were very lucky to have him here. He was connected to us through another Dr. Raymond. Yes, a family relation, in fact, but I want to thank that Dr. Raymond for bringing us Dr. Peter Raymond tonight. And thank you all for coming. You can either unmute and clap if you like, or there are little Zoom reactions we can give Dr. Raymond a little clap. And yes.
Yeah.
Yes.
Have a good spring.
Thanks so much. Yes, have a good
Yeah.
spring. We hope to see you at future RJD events, and everyone take care and take care of the planet.
Yeah.
Thank you.
Thank you.
Thanks a lot.